All right, so let's continue. This is what we had. How to resolve this optimization problem? Again, as soon as you can find something like that, you as a machine learning person or as a computer scientist or as a data scientist, you have done your job, okay? It's a convex optimization problem subject to some conditions, and this is definitely we can solve it and find the minimum of that. It guarantees, because as I mentioned, it's convex, it has a global minimum, we can find it. But how to solve it, it's completely optional. I put the slides here for your information if you are interested in, and by optional I mean I don't expect you to know details, and there will be no questions in the exam, but feel free to review it if you are interested in. We use this type of equation specifically in optimization. They are called quadratic programming with linear constraint. It's obvious, right? It's quadratic, so look, it is quadratic problem. It's called this is a standard name in convex optimization, and your strengths, which is this guy, is linear. We can use Lagrange multipliers to solve this problem, and I'm gonna skip these things. Okay, just this I wanted to mention is that in equations, eventually after you solve this problem, you will see something like that. It's still optional, okay? This is how you find your weight and your bias. So remember, the line that we are looking for was like that, like this, okay? This is our line, our classifier is this. So we need to find W and we need to find B to find the line. So here you go. After solving Lagrange multipliers, I have B and W. And it's equal to something. These are Lagrange multipliers, but it turns out that this is something good to know. It turns out that only for support vectors, okay, only for those vectors that are on the border, this value is not 0. Okay, it means that weight, this guy that you need to find the line, you just need to have those support vectors to know it. Okay, so if this is your classifier, okay, and you have a lot of data samples here, okay, so suppose that this is your margin, okay, only these samples that we call them support vectors, only these samples really matter to us, because only these samples will help us find your classifier. Other samples really, they don't contribute in finding this line. That is why we care a lot about these samples. All of those equations can find the line only based on these samples that are on the border. But the problem is that we don't know which one of them are support vectors, in fact. So we need to try all of the samples to see which one is support vectors. And this is the problem of solving SVM equations. Finding the line means figuring out which one of these samples are support vectors in your training data. So this is our training data. We have hundreds of samples. The process of finding which one of these samples are your support vector is your training. This is the process of training. That's it. So support vectors are the samples which lie nearest to the classifier. We just need to know them. If we know them, then finding this is very easy. So this is something to remember. So by solving this problem, we will find the best. Again, you don't need to remember this equation, but we will find the best line. This is our line. The best W and B, and of course the middle line, which is this, will be our best SVM classifier. This was training stage. In testing, you just need to compare that your new sample. When your new sample comes, put it here. If it is positive, you predict yes. If it is negative, you predict no. Whatever your label is, doesn't matter. So in fact, the sign of this will be our classifier. So this will be your classification rule. Look, everything gets very simple. When you have it, just sign off this guy. Okay, just sign off this can let us classify our samples. If it is positive, we predict rainy. If it's negative, we predict sunny. Remember that in different machine learning problems, in many of them that are originally a classification, we can find some good ways to convert them into a regression problem. So for example, random forest, okay? Random forest, it makes decision based on results of, for example, 100 trees, okay? Majority of them. So if 100 trees, like 70 of them say not cancer, 30 of them say cancer, then we predict cancer or not cancer. 70 of them say no, 30 of them say yes. So because majority is this, we say no. Okay, so this is, in fact, random forest is a binary classifier in this way. But at the same time, we can interpret these votes and say this is no. It means that there is still 30% chance of yes, 30% chance of cancer. Okay, so by doing this part, in fact, I converted a classifier into kind of regressor, right? Or I did that for logistic. So this was for example, random forest. So the rate of the trees that vote yes or no can give me some idea about the continuous value outcome. And we did that for example, logistic regression too. For logistic regression, your output technically should be 0 or 1, but before sigmoid function, so before binarizing the data, we have a value which is in the range of 0 to 1. After your sigmoid function, we can interpret that as a probability. So we can say when the value is 0.7, right, your output prediction will be yes, but at the same time we can provide 0.7 as a probability of happening that. So in SVM, we can do this too. So originally, it is a classifier. We always say if it is positive, predict yes. If it is negative, you predict no. But you may notice that we also have support vector machine regression or regressor. That works based on the value of this guy. Okay, so the value of this before comparing to 0 or 1 can also provide some information that can help us interpret how sure we are about being positive or about our prediction. Okay, yes, it is positive, but is it like this much positive, or it is like this much positive? Okay, so they are different. The value of this guy provides some information about maybe the probability, and it's not exactly probability like logistic regression, but certainty about your prediction. We can talk about this later. But if you see support vector machine, I'm gonna talk about non-binary support vector machine today, but if you also see support vector machine regressor, this is how it works, but the idea is the same. Let's continue. So this is our SVM classifier. Now after we find the area and W and B, now we don't care about these two lines anymore. These were the lines that help us build this classifier, and these samples on the border are called support vectors. That they were all I needed, and technically, to find this area. After building that, this only I care about the middle line, which is this, which is my classifier from now on. Okay. All right, this is what I just mentioned again. On the maximum margin hyperplane is completely determined by those samples which lie nearest to the border. They are called support vectors. So remember these things, because these are questions in job interviews. Okay, you should understand how it works. Okay, so how you have to, okay, you don't need really to know how to solve, for example, that optimization problem and like Lagrange multipliers, but this is so important for you to know what was the idea behind SVM, how we build this classifier, what are these support vectors, and all we need are from now on, okay, all you need technically are these samples of these samples or this equation. Okay, so you don't need these parts anymore. Again, this is unlike some other classifiers. So for this is called this type of machine learning algorithms are called parametric machine learning algorithms. So when you build your classifier, only this line, this equation is enough for you to make prediction in future. So only these three samples, for example, on the line is enough, or only this equation is enough. We don't need these training samples anymore unless you want to retrain your classifier. But for some machine learning classifier, for example, KNN, this is non-parametric classifier. So always when you have a new sample like this, you again have to find the distance to all of the training samples and see what are the, for example, 5 nearest neighbor. So you technically, most of the time, you need to keep the whole training samples with you to be able to make prediction. Those machine learning algorithms are called non-parametric. All right. So there are two things to remember that we will use later, especially when I want to talk about nonlinear classifier. Everywhere I have inner products that I talked about before. So that the prediction is made by computing the inner product between the test sample X and the support vectors. Okay, so in prediction stage, you don't need anything else. You just have inner product between your testing samples, which is new, and your support vectors, this guy. Okay, this is inner product. And to solve the problem, to find the W, so this, look, this is the prediction part. When you want to predict something, this is inner product between new samples. And but in finding the best line, I mean in training stage, we calculate inner product between all pairs of training samples to be able to find the support vectors. Okay, so everywhere we have only inner product, remember that. Why is this important? Not now, but later when I talk about nonlinear SVM, you will see that this is important. I will review that again when I want to talk about nonlinear. So far so good, but there's a problem here. So far, this is what I did. I solve an optimization problem. By solving that optimization problem, I found this line. Okay, but in that problem, what I did was that I made sure that every red sample are on the left hand side of this line, and I made sure that every blue sample are in right hand of this line, and also I made sure that this distance between these two lines are as large as possible. Okay, this was what I did so far, but there is a big problem. So far I assumed that all of the red ones are on the left hand side of a line, an arbitrary line, and all of the blue ones on the right hand side of another a line, and I tried to find that line. But this is not a common, this is very rare to see a data set that is that much nicely separable. Usually it's not like that. Usually you will see a red one here and a blue one here. Now what I can do? So all of the equations that I have developed so far, they are useless. All of them. Okay? Why? Because I add some constraints. So let me go. This guy. So look, this is my problem that I try to resolve. I want to maximize this or minimize the reverse of that, such that this. So this is the constraint. This is called constraint for your optimization problem. It should be always true for all i's. Okay, so in fact, for all of my data samples, I want, if it is positive samples, the samples should be on this side. If it is negative samples, should be on this side. Okay, so this is a rule that I cannot, according to this equation, I cannot violate. So I want it to be like that. Okay, but if I have a sample like this, a red one right here, only one outlier, or one bad sample, or one difficult sample, or one sample that is not that we are not able to classify it using a linear line or whatever. Because of this, those constraints will never happen, will be satisfied. So we cannot solve the problem only because of one sample. All right. So for the sake of simplicity, we have assumed that all of the data samples are separable. This approach is called hard margin. So we make sure that everything are on the correct side. And this is not good. How about not separable samples? How about this situation? When I have one sample right here and only one is enough to make all of our previous equations useless. Another blue one here. How about that situation? And remember, I talked about this before. Your classifier should tolerate errors, should tolerate bad data samples. Otherwise, it's useless in practice, because in real life, we always have samples like that. First of all, in real life, usually the data is very mixed, okay? So you cannot that simply classify samples. So you will have a lot of reds here, usually, in real life data, okay? But even if you have one, your algorithm should, even if you have one, this setting of SVM that I developed, it doesn't work anymore. Because it wants to make sure that everybody must be on the correct side. It cannot tolerate even one sample on the wrong side. Remember, I mentioned, if you remember, I mentioned this several times. Your machine learning should tolerate outliers and bad data and bad samples and difficult samples. And it should be able to take care of them, although in many cases you make a wrong prediction for them, but it should be able to work despite of having outliers in your data set. So what is the solution? So of course, we don't want to start from scratch, okay? I don't want to ruin my model that is very good, very well structured, only because of some outliers. So I have to find a way to deal with those samples. To do that, I defined some new parameters called slack variables. So again, another keyword to remember, slack variables. And in literature, they use usually this Greek letter called xi to show a slack variable. So the first people that developed this algorithm, they used this letter, and other people after that, they all used this letter. So this is a pretty standard letter to show this slack variable. It will allow my machine learning model to do some misclassifications, okay? So in fact, with this slack variables, I allow misclassification of a few difficult or bad noisy data samples, okay? So this is the slack variable. So look, this red one, this guy, this sample, and this was supposed to be on this side of the line, okay? This side of this line, remember, the red one was supposed to be on left hand side of this line. Now it is here, so this green distance is my slack variable for this sample. It means that, right, this guy was supposed to be on this side, but I let him be off by this value, okay? Or this guy, this blue sample, yes, it was supposed to be on this side of the line, but I let it be on the other side of the line. By how much? By this value. It's like a discount that I give to this specific sample, okay? This is called a slack variable. So instead, we define a slack variables xi to allow misclassification for a few difficult or noisy samples. In fact, we cheat, right? A little by relaxing our criteria and allow some of the data samples to be on the wrong side of the line. Some of the data samples like this guy and this guy, we let them be on the wrong side of the line. By how much? By this much, okay? By the value of a slack variable. However, it cannot be too relaxed, otherwise the classifier doesn't work. So I have to make sure that these xi variables will be as small as possible, okay? Because I don't want to let everybody be on the other side. So this way we will keep our previous models and just let it tolerate some errors. However, remember that we still need to minimize this amount of error, okay? So it cannot be too much flexible, right? So we have to put some restriction or minimization on these xi variables, on these slack variables. We can have some penalty on that. This approach is called soft margin, okay? Hard margin versus soft margin. Remember that this is an interview question. So this is what everything changes. So this was my original problem. It's called hard margin. I minimize this subject to this rule. So in fact, I make sure that everything is on the correct side. But look at this approach. Let me explain this. This is so important to understand this correctly. So this was the rule originally, this guy. Look at this. And this guarantees that everything on the correct side. So this will be definitely more than or equal to 1. So it will be definitely on the correct side of this line. Now I say more than 1 minus something, okay? So I make this condition a little relaxed by making this threshold less than 1. Okay, so everything should be on this side of the line. Everything should be more than 1, but minus something. 1 minus something. In fact, I would say everything should be on left hand side of this line, okay, but minus some variable to make this condition a little more relaxed, this guy. All right, so using this way, I well remember that this xi is unknown, okay? It's unknown, so I don't know what it is. I add a new variable here. So I will make this way, I will make this constraint, this condition a little bit more easy, a little bit easier, more relaxed. But at the same time, this guy cannot be anything. It should be small, it should be minimum. So that is why I put it here. I will also add it here inside my minimization problem. So before, my minimization problem was only this part. Now I also add this part, okay, to make sure that this relaxation will be as small as possible. It cannot be anything. It cannot be infinite. To be honest, it is a very smart way, right? They did a really nice way to make it relaxed, but at the same time not too much relaxed. Okay, so the condition will be easier, not too easy, because this, guys, the length of this green line, this length will be a part of minimization problem, so it should be as small as possible. I will explain. I have not explained that yet. I'm gonna talk about this now. But the C is in fact a value that let you make a trade-off We have something like that in every machine learning algorithm. So it is a trade-off between how tough you want to be in tolerating these outliers. Okay, I'm gonna talk about this. But generally speaking, the idea is that this was our original constraint. I wanted everything to be on one side of the line. By minus xi, okay, I make it a little bit more relaxed. Let some of the samples will be on the other side of the line. So for some samples, for example, whatever, like x5, if this value of xi, I don't know what it looks like, xi5 is, for example, 2, if this guy is 2, it means that I will let sample 5, this guy, let's call it sample x5, be not greater than 1 but greater than -2. So I will let it be on the other side of this line even. Okay, but at the same time this value should as small as possible. Let me explain C. Okay, C is the most important factor is in adjusting an SVM classifier. It's a very important parameter, and you should understand it very well. Okay, there will be very important to adjust it in making your good classifiers. And as I always mention, there are some parameters in every machine learning model that we have to adjust, right? Okay, so for example, people who are not computer science or data scientist people, they prefer simple algorithms that doesn't have too much or too many parameters to adjust. Okay, like SVM. So SVM, technically this is the main parameter that you have to adjust to be able to build a SVM effective algorithm. But for artificial neural networks, there are a lot of parameters that you have to adjust. Okay, so having more parameters will make it a little bit more difficult to adjust your model, but it gives you a lot of flexibility. So it's like a more professional algorithms. So C here, it's technically defined a trade-off between how accurate you want your classifier be and how relaxed your algorithm want to be in tolerating wrong samples and outliers. Okay, so look, for example, if you select a large C, it is like a penalty that you put it here. Okay, remember, I want to minimize the whole thing. Okay, I want to minimize this guy. So let me show you this. If I want to minimize, okay, A plus B, two variables. Okay, I treat them equally. So I want to make this small, and at the same time I want to make this small. I want to minimize the whole thing, so I want to make A a small and B a small with the same rate. Okay, but if I say minimize A plus, let's say 10 times B, okay, this is an extra penalty on B. I penalize B. It means that I want to make A a small, but I want B to be a small 10 times more. Okay, so if it's in the range of 5, for example, this guy can be in the range of 0.5. Okay, so I add 10 times penalty on B because I want B to be 10 times smaller than A when I run this. Okay, so this coefficient here is a penalty on B. This is the same thing here. So when C is large, Okay, this is so important for you to understand this. When C is large, in fact, we penalize xi more. It means that we want the xi to be very small and small and small. Okay, so no tolerance for misclassification. Okay, no flexibility. I want to make sure that it is like when you increase C, you want to make sure that everything will be classified correctly. You don't tolerate misclassification. It means that your model has low bias, high variance, and it will be prone to overfitting. All right. So when you increase C, you add more penalty on xi. You will make sure that xi is very small. Okay. So you don't tolerate misclassifications anymore. It makes your model very low bias. Okay. You remember in overfitting, I talked about exactly these things. So these are some samples that you have. Okay. Your overfit model. So when your model is not overfit, okay, when your model is not overfit, it can be a line like that, for example. Okay. But when your model is overfit, it does not tolerate any misclassification. So you come up with some classifier like this. Okay. This is an overfit model. So when you make C large, okay, when you increase the value of C, you add more penalty on this poor guy. So this will be a small to make sure that the whole thing will be satisfy this rule. So it does not tolerate misclassification anymore, low bias, high variance, and it will be very prone to overfitting. Okay. So to solve, it's overthinking, right? Overthinking in AI, in artificial neural networks, overthinking. On the other hand, if you make this C small, okay, it will let you make xi a little larger so that the whole thing can... There's something wrong with my pen today. So when you make this guy a small, it will let you make xi a little larger so that this guy can satisfy this rule. Okay, so smaller C right here means let larger xi allow for misclassification, so it's like increasing this value xi. High bias, low variance, it will be prone to underfitting. Okay, so simply by adjusting this C, you can make your model less overfit, or you can adjust if it can tolerate misclassification or not. If your model is overfit, you have to reduce this C. Remember that. So look, so far I just talked about binary and linear SVM. Okay, let me talk about multi-class classification with SVM. What if we have more than one class? And next week I am gonna talk about non-linear SVM. Okay, non-linear classification, which is actually technically it's just a modification to linear. Okay, using a technique called kernel trick. Okay, kernel trick, using a technique of kernel trick, we just modify our linear SVM to non-linear SVM. And non-linear SVM models are very effective, very accurate in classification. So let me talk about this first. So SVM is originally a binary classifier. So far I just assume that there is a line, something in this side of the line, something in other side of the line. Okay, so far it was binary. But technically you may have more than one label, okay, like 3 labels, setosa, versicolor, virginica, or other things, okay? For any data you may have more than 2 labels. So the best approach for SVM to handle non-binary labels is a method called one versus all, okay? And we can apply it for all classifiers that are originally designed for binary classification. For example, logistic regression, okay? Logistic regression is another one. So suppose that I have 4 different labels. I will try 4 different rounds. In the first round, I called this label 1, and I called all 3 of them together, combination of them, this is label 1. I called 3 of them together label 2, okay? And find a classifier that classifies 1 versus all others. This will be my line, okay? In the second round, same thing. I put this as 1 label and I combined everything else as the other label 2, and find the best classifier to classify purple versus everything else. So this will be my classifier 2, and repeat these things 4 times. So I create 4 different classifiers, okay? 4 different lines. And then in the testing set, when you want to predict something, the new sample X, when it comes, I try all of these 4 lines on that new sample, and the ones that give me the largest value will be the label that I select, okay? So in this approach, assuming that we have k different labels, so in this example k is 4, we train 4 SVM classifier, one to distinguish class K from the rest. Each one of them give me a line with some W's and B's. Okay, so for example, W1 for classifier 1 and so on. Then in the testing set, for a new sample X, pick the class with the largest value of this. Okay, so this is how it works. This is called one versus all method, and we can apply it for every originally binary classifier and to run it on multiple labels. And scikit-learn automatically does that for us, so you don't need to implement this process. Okay, SVM in Python, we have linear and non-linear models. So non-linear, I will talk about this next week, okay? So next week we will cover this, and also dimensional reduction, principal component analysis. And after that, we will return back to artificial neural networks, and the rest of the semester will be on deep learning. So the codes are very simple. The same in scikit-learn, same structure as other machine learning algorithms. So from sklearn SVM, import this guy, linear SVC, support vector classifier. Here, when you define it, you can define your parameters right here, okay? So for example, C is one of the parameters that you can define here, and also there are some other parameters that, for example, random seed and so on, and then train and test. When you want to work with nonlinear, I will cover the theory of that next week. Import SVC. Parameters, in addition to this standard parameters, you also need to define kernel. Okay, that I'm going to talk about this next week, but in the meantime, if you want to use nonlinear classifier, nonlinear SVM for your project, I recommend to use RBF. As your kernel. Okay, so you have to define kernels. It will give you several options, and RBF is one of the ones that provides the best results if you want to use it for your project in the meantime.